Now, in terms of your equations for the photoelectric effect, we need to first define something referred to as a work function. And the work function is basically just the minimum amount of energy required then to release the electrons. Now, in terms of this one here, that minimum amount of energy will occur then at a minimum frequency or a maximum wavelength. And so just be aware that those two are going to be going in opposite directions. And that's just because ultimately it is the energy that we're looking for. And so we're looking for a minimum energy of light that's required then to remove those electrons. That minimum energy is going to occur at a minimum frequency because frequency increases with energy, but it occurs at a maximum wavelength because wavelength decreases then with increasing energy. And so just remember that in terms of the energy, the frequency and the wavelength do have different trends. And so high energy light has a high frequency, but it has a very short wavelength. Low energy light has a low frequency, but a very long wavelength. And so when we're talking about this work function, we can define it in terms of either a frequency or a wavelength. When we define it in terms of a frequency, it's a minimum frequency. When we're defining it in terms of wavelength, it's a maximum wavelength. So just be a little bit careful for that. Now this is empirically derived, so it means we have to just go into the lab and test it. And to do that, we just shine different frequencies of light on the metal until some electrons are released. Now to get the equation for this, and this equation here, this HF naught equals work is given on your formula sheet, but where it comes from is just conservation of energy. The energy of the photon coming in has to equal the energy given to the electron. Because the electron's absorbing the photon, the conservation of energy is going to apply. So the energy for the photon, we'll just use Planck's equation for that. So the Planck's constant times the frequency, and that'll equal the work required to pull the electron off the surface. So HF naught equals the work function. This capital W is the work function. That can be in either joules or electron volts. So it's just really an energy unit there. H is, of course, Planck's constant. Just make sure it's matching up to your energy unit. And then this F naught is the threshold frequency. And so that's your minimum frequency for the electrons to be released. And if your light is below that frequency, no electrons are coming off. Now we do also have that C equals frequency times wavelength equation. And so we can then substitute that frequency for a wavelength. And so frequency equals C over wavelength. And so I can also define my work function in terms of HC over then that threshold wavelength. And don't forget, that's going to be a maximum wavelength. And so because we can define the energy of light in terms of either a frequency or a wavelength, we can talk about then threshold frequencies or threshold wavelengths. This one's not on your formula sheet, but make sure you know how to derive it from the one that is given. Now, very often the light that we're shining on the metal will be greater than the threshold frequency. And so as long as you're at or above the threshold frequency, those electrons are coming off. But if you're using a light that has a greater frequency than the threshold frequency, that means that you do have some extra energy. And that extra energy then is going to show up as kinetic energy in those electrons. And so that will give us then a third term when we're looking at our conservation of energy. So what we have is we have these incident photons. That's going to be basically my initial energy over here. And then that gets absorbed by the electrons, so that's the final energy. Now, some of the energy that goes to the electrons is used up in just pulling it off the surface. So remember, those electrons are stuck to the surface, so if we're removing those, that requires a certain amount of energy. That's going to be my work function. And then any extra energy that came from these photons, that's released then as EK in these ejected electrons. And so my electron energy, which will be my final energy, so it's just energy initial equals energy final, that has two components to it. The work function, which is the energy required to remove it from the surface, and then the kinetic energy that it's left over. So all of the photon energy is going to the electrons, but in the electrons, that's showing up in two different components, because again, some going into pulling it off the surface, and then some going into its excess kinetic energy. So this equation here is not on your formula sheet, but it is one that you'll use to solve a lot of these problems. So it's coming just from conservation of energy, but make sure that you can put this one together. The energy of the photon is equaling then the energy of the electrons, which is broken up into work function and kinetic energy. Now from here, you can do a number of different substitutions. Now sometimes you might just be finding the work function, the kinetic energy of the electrons, or just the overall energy for the photon. But remember, you can use this to find other things as well. So this W here for the electron, that one then can be split up into threshold frequencies or wavelengths. And so you could substitute either of these equations in for there. So HF naught or that HC over wavelength naught. The kinetic energy of the electrons, don't forget kinetic energy is just 1/2 mv squared. So very often you might be solving for that kinetic energy of the electrons, but you could also look for, say, the velocity of the electrons being ejected from the surface, and that would be possible as well. And then the last one, the energy of the photon, that's that incoming light energy. That can be defined as either HF, so if you want the frequency of your incident light, or hc over lambda if you want the wavelength then of the incoming light. Now, one other piece then that we can add into this is something called a stopping voltage. And your stopping voltage comes from basically how we determine then the energy of the electrons. So just going back to here, this is the standard photoelectric effect experiment, but I've added just a battery over here that's going to be opposing then the release of electrons. So remember, if this battery isn't there, these electrons are basically coming across there. They have some kinetic energy when they leave the surface, and they're heading then for this wire to complete the circuit. However, if I put then an opposing voltage here, that's going to be an electric potential going then, or working against that electron. And so what I can do is then set up that potential difference then to here, which is then a potential energy, and I can make that equal to the kinetic energy. Now, if the kinetic energy is higher than this potential energy, then the electrons will still get through. But if the kinetic energy is equal or lower to this potential energy, then the electrons will be stopped. And so then we can say that the kinetic energy of those electrons will be equal then to the minimum potential energy required to stop those electrons. And that's something we call the stopping voltage. So the minimum voltage required to stop the electrons can be related to that EK max. And so that kinetic energy and that conservation of energy term from just previous there, that can be also in terms of the QV stop for those ones there. Now you will see, and this equation's on your formula sheet as well, we do say EK max, and that's just because we have different electrons in the metal. So some electrons are on the surface and some electrons are further in. The electrons on the surface require the least amount of work to come off, and so those are going to be the ones that have the highest kinetic energy. Now we might have a high enough energy source here that some of these inner electrons are coming off as well, but because they use up more energy getting off the surface, they have less kinetic energy when they leave. And so what we're trying to get is we're trying to stop all of the electrons. And so this EK max, that's going to be these surface electrons that have the highest energy. If we can stop those, we stop all of the other ones as well. So your calculations for these questions here are typically going to involve that conservation of energy equation. And so for this one here, we have a surface being illuminated with light of 500 nanometers. So that's going to be then the energy of the photons. We have a binding energy for the electrons. Now, binding energy is just the work function. So that's going to be 2 electron volts. And remember, those can show up in electron volts or in joules. And we're looking for what voltage then is going to be required. So it's going to be a stopping voltage to protect or prevent those electrons from being emitted. And so for this one here, we'll start with then just that equation. The E of the photon must be equal then to the energy of that electron. And so it's always going to be that conservation of energy. And that's going to be the key for solving then photoelectric effect type equations. So the energy of the photon, now I can have HF or HC over lambda. Here I have 500 nanometers, so I'm going to want the one in terms of the wavelength. So I have HC over the wavelength. I know that's for the photons coming into the, or onto the surface of the metal. Now the energy of the electron, I have a work function that's going to be removing those electrons from the surface. And then I have plus EK. Now that's the kinetic energy of the electrons. Now remember, I'm using a stopping voltage in this case, so that EK of the electrons is going to be equal to that QV stop, and so I can substitute that in then as well. So I'll have HC over wavelength equals then the work function plus QV stop. And so my stopping voltage then is going to be related to that QV, so I'll get QV for that stopping voltage. Now that'll be equal then to HC over wavelength minus the work function. And then of course I can isolate that voltage. That'll be the stopping voltage. That'll be HC over wavelength times Q minus W, then the work function, also divided by Q. So do make sure when you're dividing out that Q that you divide it by both terms. And now to find my stopping voltage, all I need to do is just put my values into the equation and I'll have the voltage there. And so I'll end up then with this 0.486 volts. Now do watch your units as you're going through here. So I have this 6.63, and I need to use the 6.63 in joules times seconds so that my units are going to cancel out. And so what we'll see here with our units is I have seconds and seconds canceling out. I have meters over meters, which is going to leave me in joules per coulomb. This one here, I have a work function in electron volts. So I'm going to first change that to joules over electron volts by multiplying by that 1.6 times 10 to the negative 19. Now that's the same number as the charge on the electron, but here I'm using it as that conversion factor between joules and electron volts. So that's why the units are joules over electron volts. Here it's the Q, so here it's the charge. And what we see here then is my electron volts cancel out, and I'm left with joules per coulomb. Now again, that works out to be then just that value of 2, but again, that's why we define that conversion factor for joules to electron volts in terms of then the elementary charge. So when I solve this piece here, I get the 2.48, that's in joules per coulomb, minus 2 joules per coulomb, so that gives me the 0.486. That gives me units of joules per coulomb, but the units of joules per coulomb, remember, are the same as volts, and so that's how we end up with the 0.486 volts. So for this question, we have platinum with a work function of 6.25 electron volts. Of course, that's for the energy of the electron, or part of that. We're looking for what wavelength of light is being used, so that's the photon ones. And we're given then a speed then for those electrons. And so your speed of the electrons, of course, will be related to its kinetic energy. So we'll start with that just overall energy equation first. So my photon energy must be equal then to the electron energy. Now my photon energy will be hc over wavelength. Now again, this could be hf or hc over wavelength. Here we're looking for what is the wavelength of the light. And so that's why we're using the hc over wavelength for that one. Now in the energy for the electron side, what we have then is we have the work function for the electron plus that Ek for the electron, which of course is 1/2 mv squared. And so my hc over lambda is equal then to the work function plus 1/2 mv squared. Now for this one here, it is going to be a little bit tricky algebraically just to isolate the wavelength at this point because I have two terms on this side. So what I'm going to do is I'm just going to put my values in for here and solve that, and then I'll take the reciprocal to solve for my wavelength. So I'll leave this side alone for right now, and I'll just solve for then the right side of that equation. So what we see for this section here is we had our work function again in EV, but when we put in a mass and a velocity squared into my kinetic energy, I'm going to get a value in joules. So I do have to be working in joules for both of those. So I multiply by that 1.6 times 10 to the negative 19 conversion. That gives me a value in joules, the kilograms meters per second squared, and the mass of the electron, of course, just from your formula sheet. That will give me value in joules as well. So now we see that my hc divided by wavelength is equal to 2.475 times 10 to the negative 18 joules. So carrying on from here, now I can take the reciprocal of both sides. That'll give me wavelength over hc equals 1 divided by that 2.475 times 10 to the negative 18 joules. And I can say I can multiply my hc to the other side, and that will solve then for my wavelength. And so when we do that, we have joules times seconds times meters per second. So then my seconds are going to cancel out overall. And then I have joules over joules. And so I'm left just with units in meters, which is what I'm expecting then for my wavelength. I'll get 8.03 times 10 to the negative 8 meters. And if you're just looking for the wavelength, that's an easy place to leave it. Because we're also looking for the region of the EMR spectrum, it might be helpful to move that into nanometers. And just remember for that one, the region that you do need to know is that 400 to 700 nanometer region. Now the 700, this kind of marks the start of that infrared region heading that way. Here your UV region is the kind of one that's next lower than 400. So 80 is lower than 400, and so that's going to put us in that UV region there. And so that's the region then from the spectrum that you're looking for there.